talk about magnets. I think we all know quite a bit about magnets. We learned about magnets in like third or fourth grade. We know we have north poles and south poles. We know that opposite ends attract and likes repel. We know that certain materials are magnetic. Iron, for example, is magnetic, others aren't. Aluminum is non-magnetic. And by that we mean that a magnet will attract certain metals. We'll talk about why that is in the next chapter. We know that the Earth has a magnetic field. Now, what we don't often think about, if we think about a compass is just a magnet that we allow to float and turn around. And by definition, the north end of a magnet is the one that points geographically north. So points towards Canada for us here in Florida. So a magnet has a north and a south pole. If you stick a magnet in water and let it float, the end that points geographically north we call the north pole of the magnet. The one that points south we call the south pole. But we also know that the north end of a magnet is attracted to a south magnetic pole. So that means that the north geographic pole is actually a magnetic south pole. The North Pole is a south pole. The North Pole, where Santa Claus lives, is a magnetic south pole because it attracts the north end of a compass. And that sounds weird. It would kind of make more sense if we had done it the other way. But this was for convenience so that we can talk about the north end of a compass pointing north, and everything comes from that. Okay, there's no such thing as a magnetic monopole. We're going to talk about Gauss's law for magnets in a future video. And Gauss's law for magnets says that the surface integral over any enclosed region of the magnetic flux is always zero. And the reason is there's no such thing as a magnetic monopole. With electric fields, we have electrical charges. We have positive and negative charges. That doesn't happen with magnets. It's impossible to just have a north pole. If you take a magnet and you cut it in half, you'll end up with two complete magnets. Each one will have a north and south pole. Every now and again, you'll hear crazy physics theories that predict magnetic monopoles. And I'm here to argue that those theories are just bunk. They're wrong. There's no such thing as a magnetic monopole. You can't have a north or a south pole alone by itself. Okay, we'll talk later about why wires create magnetic fields. Moving charge creates a magnetic field, which will deflect a compass because it's two magnets interacting with each other. Magnetic fields, like magnetic forces, are created, obviously, by magnets, but magnetic field lines don't start or stop. Electric field lines start at positive charges, end at negative charges. For magnets, we don't have charges. There's no such thing as just a positive magnetic charge. There's no place for a magnetic field line to start. Magnetic field lines never start or stop. They pass right through a magnet. We'll talk about that in the next chapter. Magnetic forces act on moving charges. We'll talk a little bit about this later, but there's really no such thing as magnets. They really don't exist. A magnetic field is really just an electric field in a different reference frame. The whole idea of magnetism is really just a byproduct of special relativity. And I'll do a video explaining that, but magnetic fields only affect moving charges. And I'm going to do a whole video on this. The magnetic force on a moving charge is the cross product of the velocity vector of that charge with the magnetic field vector times the charge. So this is for any charge. Positive charges follow the right-hand rule. Negative charges follow the opposite of that, or we could say the left-hand rule, but it's better to do right-hand rule and go backwards. So I'm going to do an entire video on the magnetic force on a moving charge. We just follow the right-hand rule. Magnetic field lines, we said this just a minute ago, do never start or stop. They emanate out of the north end and go back around, back into the south end and go straight all the way through the magnet. They don't start or stop. They never intersect. They are not lines of force. No particle will ever move along a magnetic field line. No matter what's happening, magnets do no work. So if I were to take any kind of particle and stick it right here on this magnetic field line, it would never follow along this line. Magnetic field lines make things rotate or change direction. They don't make them move a particular direction. So if I were to put another magnet in this magnetic field, that magnet would rotate. It would not move along the line. Okay, we'll talk again next chapter about why this is. But if we have a current is created by moving charges. That's what current is. Moving charges create magnetic fields. And this is what the magnetic field would look like from a constant current. A bunch of circles that go around that current. And these would keep going. There'd be circles here and so forth. And we'll talk about what these symbols mean out of the plane into the plane. Magnetic flux is just like electric flux, the same idea. It's the contribution of the magnetic field perpendicular through some surface. So if I've got some magnetic field at some angle here passing through this surface, then the magnetic field is the perpendicular contribution of that field, or the magnetic flux, is the perpendicular contribution times the area. So in general, magnetic flux is the surface integral of B dot dA, just like electric flux. When we did Gauss's law for electric fields, was E dot dA. Now we have B dot dA. But because there's no such thing as a magnetic monopole, for any closed surface, the total flux through that surface will always be zero. For a closed, bounded, simple surface. Magnetic field is measured in Tesla. Now you hear a lot nowadays about Nikola Tesla as though he were the greatest physicist that ever existed. That is really, really not true at all. The guy had some good ideas early in his career, but by the end of his career, he was a quack. He didn't believe in relativity. He didn't believe in quantum mechanics at all. He argued with Edison. He argued with Einstein. His idea of free energy, what we call broadcast power, was completely untenable. He was not the savior of mankind that people make him out to be nowadays. He was not a very good physicist at all. He was an okay engineer, but he was not as brilliant as Einstein, not even in the same field as Einstein. Magnetic flux is measured in Webers. Okay, so if you put a charged particle that's moving with some velocity v in a constant magnetic field, and I'll draw some pictures of this in another video, that charge will just go in circles because magnetic field lines or magnetic field forces change particles' directions. They don't speed them up or slow them down, they just change their direction. And we get what's called the cyclotronic radius. If you have any homework question that asks you for a radius of a circle, when you're dealing with magnetic fields, you're looking for the cyclotronic radius. Now, if we have some kind of two-dimensional motion, we could get a helix. So, we see these in bubble chambers. At the high energy particle colliders, this is how we find new particles. We put particles in this giant accelerator, we slam them into each other, they break apart into smaller particles, or they combine together into larger particles, and we have them in this magnetic field, and we watch how they move. And from this, we can... My mouse is not working properly. From here, we can look at this spiral and figure out what the mass and the charge of that particle must have been. That's how we discover new particles. Okay, and then we really won't do much of this. Okay, torque. So, again, we'll do some more videos where I can show you with my hands what's going on here. But if I have a current floating, going around some loop in a magnetic field, that magnetic field will push on these lines. Magnetic fields cause forces on moving charges. So this side will move maybe out, whereas this side will move back, and we'll get a torque. So if I put a current in a constant magnetic field, and I do it just right, I can make this thing rotate. Oh, that's called a motor. So here's how we build a simple DC motor. And again, we'll play around with these a little bit later.